Track 4, Performance and Limitations. The pre-flight weather briefing complete, the examiner now shifts gears to see how Robin determines the aircraft's performance and limitations.
Okay, Robin, now let's talk about today's weather and how it's going to impact the airplane's performance. How does today's weather relate to standard atmospheric conditions at sea level, and why do we need to consider this?
Standard atmospheric conditions are 15 degrees Celsius and 29.92 inches mercury. We're a little warmer at 25 degrees Celsius, with the pressure a little higher at 29.96. But we aren't dealing with anything like high-density altitude conditions. It's good to know how today's weather compares to standard atmospheric conditions because your aircraft's performance numbers are derived under specific conditions that may not apply to your particular flying day. An atmospheric standard is just used as a baseline to find accurate performance data.
What is pressure altitude and how is it useful?
Basically, pressure altitude is useful for determining aircraft performance. I compare a given day's altimeter setting with the altitude I get when selecting a standard day's altimeter setting, and this gives me meaningful performance numbers that take into account differing barometric pressures. So to find pressure altitude, I just dial in 29.92 and read the indicated altitude.
You mentioned a concern for density altitude when you compared today's conditions against standard. What is density altitude?
Density altitude is pressure altitude corrected for non-standard temperature. Basically, it refers to a hypothetical altitude that represents what kind of performance you would expect under given conditions of air density. In other words, density altitude reflects how an airplane would act under given conditions. At a high density altitude, the airplane will act as though it was actually at that altitude, even though it may just be hot at sea level.
What factors affect air density?
Altitude for one. The higher the altitude, the less dense the air. Also, temperature has an effect in that the warmer the air, the less dense it is. Finally, there is humidity. The more humid, the less dense the air. I need to be particularly concerned at airports that are high, hot, and humid. This is where I'll find high density altitudes and therefore lower aircraft performance.
How can you determine what the density altitude is today?
Well, two ways. I can use my flight computer to determine this by simply plugging in the pressure altitude and outside air temperature. Or I can use a density altitude chart. Today's density altitude at Arlington is 1,867 feet.
Okay, how does air density affect aircraft performance?
The air density will affect the amount of lift produced by the wings, the power output of the engine, the propeller efficiency, and the total amount of drag. An increase in density altitude results in an increased takeoff distance, a reduced rate of climb, an increased true airspeed on approach and landing, and an increased landing roll distance.
What factors, Robin, cause the difference between indicated airspeed and true airspeed?
Temperature and pressure altitude. As you fly higher in the atmosphere, true airspeed increases over indicated airspeed.
How would this higher true airspeed at altitude affect your approach and landing if we were at a high density altitude airport?
The indicated airspeed used on approach and landing won't change with altitude because the airspeed indicator senses the same drop in air density as the wing. However, because true airspeed is higher, it means my airplane will actually land at a higher airspeed than indicated, so I'll need to allow for that in my planning as the landing distance will be increased. The same is true for takeoff. Takeoff distance will increase.
How about today's winds? What effect will these have on the aircraft performance?
Today's winds are pretty light on the surface, 340 at 10 knots, and much stronger but in the same general direction at 6,000 feet from 350 degrees at 33 knots. For takeoffs, a headwind increases airplane performance by shortening the takeoff distance and increasing the angle of climb. A tailwind decreases performance by increasing the takeoff distance and reducing the angle of climb. For landings, a headwind increases airplane performance by steepening the approach angle and reducing the landing distance. A tailwind decreases performance by decreasing the approach angle and increasing the landing distance. For cruise flight, a headwind decreases performance by reducing ground speed, which increases the fuel requirement for the flight. A tailwind increases performance by increasing the ground speed, which reduces the fuel requirement for the flight.
Okay, Robin, what performance charts did you use in today's pre-flight preparations?
I used the takeoff distance chart to calculate my normal takeoff ground run. If I had an obstacle to clear, I could also calculate obstacle clearance ground run from this chart. I used the rate of climb performance chart to calculate rate of climb. I also used the time, fuel, and distance to climb chart to calculate what it would take to climb to cruise altitude. The cruise performance chart was used to calculate percent brake horsepower, true airspeed, and fuel consumption. And I used the landing distance performance chart to calculate my normal landing distance, as well as distance required to clear a 50-foot obstacle at my destination.
Will the performance charts always provide accurate information concerning aircraft performance?
For the most part, yes. But there's a lot of variables that affect the performance stated in the charts. The information they provide is based on flight tests conducted under normal operating conditions, using average piloting skills with the airplane and engine in good operating condition. Any deviation from those conditions will affect performance.
And what affects the performance of an aircraft during takeoffs and landings?
Air density, surface wind, runway surface, upslope or downslope of runway, and weight.
Okay, Robin, show me how you arrived at the numbers you have in your flight planning here.
For the takeoff distance chart, I had to know the pressure, altitude, and temperature in Celsius. I found gross weight in the first column, then I found the pressure altitude column corresponding to the weight. Ground roll was 765 feet, and total distance to clear a 50-foot obstacle is 1,420 feet. I have a headwind component of 10 knots, so I decreased those distances by 10%. I did the same for my departure from ABI. These distances are well within the available takeoff field lengths of both airports.
Besides the adjustments you made for the headwind, what other factors will change the required takeoff distance?
The notes on the chart indicate the stated performance is achieved using a short field takeoff procedure, flaps at 10 degrees on a paved, level, dry runway.
Okay, how did you calculate your time, your fuel, and distance to climb to your cruise altitude?
Okay, I located the departure airport pressure altitude and noted the time, fuel, and distance to climb values. I also adjusted the values by 10% for non-standard temperature. Then I obtained time, fuel, and distance values for my final cruise altitude, also adjusting for non-standard temperature at altitude. By subtracting the departure values from final cruise altitude values, I determined the amount of time, fuel, and distance to climb to my cruise altitude.
Not bad. Any special notes for the time, fuel, and distance to climb chart?
Yes, I must increase time, fuel, and distance by 10% for each 10 degrees above standard temperature, and all distances shown are based on no wind conditions. I adjusted for those, as you can see here.
Now, how did you get your numbers from the cruise performance chart?
First, I located pressure altitude, then the engine RPM I intend to operate at, and noted the true airspeed and fuel consumption rate for that altitude.
And the landing performance chart, what did you find out there?
The runway lengths are more than adequate for us today, adjusting for the 10-knot headwind on landing, a ground roll of 480 feet, and I'll need 1,094 feet to clear a 50-foot obstacle.
Okay, let's talk about how you calculate the amount of fuel we'll need for today's flight.
Well, I used the airplane's cruise performance chart to determine an approximate fuel consumption during the climb, en route, and descent phases of flight. I don't know for sure this airplane burns exactly that amount, and we'll have a better idea when I refuel as to how close the charts are to the actual gallons per hour burned.
How did you arrive at the total fuel burn figure?
As indicated in this section of my flight log, I calculated 10 minutes and 1.5 gallons for taxi and takeoff, 11 minutes and 1.6 gallons for the climb to my en route altitude, 1 hour and 6 gallons used for en route cruise, 10 minutes and 1 gallon for the approach into Abilene, and another 30 minutes and 3 gallons of gas for the VFR day reserve. This adds up to a required fuel figure of 13 gallons.
Looks like we have more than enough fuel for today's flight, but what are several factors that may affect the accuracy of your calculations?
Winds aloft can have the most significant effect. If a headwind exists that wasn't forecast, the time en route increases along with the amount of fuel required. Also, whether or not I choose to lean the mixture during flight, the condition of the engine, the percent horsepower I actually operated at, all affect the amount of fuel burned.
Okay, what about crosswinds? Show me how to calculate the crosswind component for the airplane today.
My takeoff will be from runway 34 and departure time wind is forecast to be 340 at 10 knots. Since the wind direction and runway direction are the same, I won't really have a crosswind component, only a headwind. I used the crosswind component chart in the POH. If the wind direction were different, I would enter the chart at the appropriate relative wind angle and follow that line until it intercepted the wind velocity line. I can read the headwind component on the right side of the chart and the crosswind component at the bottom of the chart.
Just a couple more questions. How does weight affect takeoff and landing performance?
Well, increased gross weight results in a higher liftoff speed, a slower acceleration, more drag and ground friction, and a longer takeoff distance. On landing, the airplane will require a higher speed to support the airplane at the landing angle of attack and lift coefficient, resulting in longer landing distance.
Explain the significance of load factor.
Load factor refers to the effective airplane weight increase that happens as a change is made to its flight path and centrifugal force is encountered. Since an object in motion wants to stay in motion, any displacement from that condition results in a force being imposed on the airplane. The term for this is a G. A load factor of 2 Gs means the airplane and occupants effectively weigh twice as much as they normally would.
And maneuvering speed, what's its significance?
This is the speed below which any additional load factor imposed upon the airframe will only cause the airplane to stall. Above VA, you can cause structural damage if any additional loads are imposed.
How is the VA, or the maneuvering speed, affected by changes in aircraft weight?
VA will go up with an increase in weight. For example, it's 92 knots at 2,000 pounds in the airplane we're flying today and 99 knots at 2,400 pounds. The reason for this is that VA is tied directly to stall speed. As more weight is put on board, stall speed increases because more lift is required to hold the wing up. This is lift that won't be available as the wing approaches the critical angle of attack. Since VA is the speed at which the airplane stalls rather than bends, it will go up too.
Okay, let's talk some more about weight of an aircraft. What is significant about weight and balance of an airplane?
Weight refers to the basic empty weight of the aircraft plus everything else that might be placed in it, such as fuel, passengers, and baggage. It's important we don't exceed the gross weight defined in the POH. Balance refers to the location of the center of gravity of the airplane and is important to airplane stability and safety of flight. The CG is a point at which an airplane would balance if it were suspended at that point.
How would you find the center of gravity location?
I use a memory jogger called WHAM, which is weight times arm is equal to moment.
Okay, Robin, how would your airplane performance be affected by an overloaded aircraft?
A bunch of ways. I'll have a higher takeoff speed, longer takeoff run, reduced rate and angle of climb, lower maximum altitude, shorter range, reduced cruising speed, reduced maneuverability, higher stalling speed, higher landing speed, longer landing roll, excessive weight on the nose wheel. Not a good effect on performance at all.
I would definitely say we want to avoid doing all of that then. Okay, tell me how rearward and forward CG affects the airplane's flight characteristics.
With a forward CG, I'd have a higher stall speed, slower cruise speed, it will be more stable, and I'll need to use greater back pressure on the yoke. With a rearward CG, I have a lower stall speed, higher cruise speed, it will be less stable.
Great. Okay, now tell me about weight and balance calculations you did for today's flight.
I prepared a weight and balance analysis using full fuel for the airplane, myself at 120 pounds, you at 180 pounds, and 40 pounds of baggage. Based on these numbers, we're well within the center of gravity envelope for the airplane and haven't exceeded maximum takeoff weight, although we are close on the weight. I used the graphs and tables provided in the aircraft flight manual to calculate the weight and balance for this flight.
What's involved in this calculation?
First, I listed the weight of the aircraft, occupants, baggage, and fuel using 6 pounds per gallon for the weight of the fuel. Then I entered the moments for each item listed. I obtained these moments by using the loading graph provided in the aircraft flight manual. I then totaled up the weights and moments. Then, using the center of gravity moment envelope chart, I plotted a line for total weight and a line for total moments. The line intersected within the envelope, indicating the aircraft is loaded within limits.
Now, during the flight, we're going to burn off fuel, and will that weight change due to the reduction in the fuel load cause our CG to change?
Yes, there will be a change, but very minor because the arm of the fuel tanks were designed to be pretty much right at the CG. But I did calculate the new weight and CG for the aircraft as it approaches our destination, and the chart still indicates we'll be within the CG envelope.
Take a look here. Looks like all your calculations are correct. Okay, let's move on and talk a little more about aerodynamics. Explain to me what causes a stall.
An airplane stalls when the critical angle of attack has been exceeded. When you get the angle of attack to about 18 to 20 degrees, the air can no longer flow smoothly over the top of the wing, and you stall.
Okay, so this occurs when the airplane's just too slow?
Actually, it can happen at any airspeed, any altitude, and with any power setting.
What about spins? What are these?
A spin is when the aircraft descends in a spiral while flying at an angle of attack greater than the angle of maximum lift. They usually occur due to an aggravated stall in either a slip or skid.
So, Robin, what would you be doing to cause a spin?
I could enter a stall with excessive or insufficient rudder, or to a lesser extent, aileron.
When is a spin most likely to occur?
A few common scenarios where a spin could occur are, 1. If I have an engine failure on takeoff during climb-out. I need to be careful not to stretch the landing glide by applying back pressure and not try to make an uncoordinated turn back to the runway at low airspeed. And 2. When I turn from base to final and in a slip or skid configuration. This might be due to overshooting final because of crosswind conditions and then trying to make an uncoordinated turn at a low airspeed. 3. If I have an engine failure on landing approach. I have to be careful not to stretch the glide by pulling back. And finally, on go-arounds with full nose-up trim or with improper flapper traction.
What factors, Robin, contribute to left-turning tendencies in an airplane?
There are several of them. First of all, torque, where the rotation of the crankshaft and propeller tries to roll the airplane in the opposite direction due to the physics of action and reaction. Then there's spiraling slipstream, where the air flowing behind the prop twists in a corkscrew shape around the fuselage. This air pushes on the vertical tail and yaws the nose to the left. Then there's P factor, where the downward moving propeller blade in a climb pitch attitude has a higher angle of attack and therefore more thrust on that side, which consequently yaws the nose to the left. Oh, and then there's gyroscopic effect, where the nose of a tail dragger yaws to the left on takeoff as the tail is brought up. As the tail is brought up, a force is applied to the top of the spinning disc of the prop, which transfers 90 degrees ahead in the direction of rotation. In other words, this precession tries to pull the airplane's nose to the left. For all of these, I counter it with additional right rudder.
Okay, Robin, I feel pretty good that you know how to determine the performance and limitations of your airplane.
Robin continues to demonstrate her operational understanding as a private pilot. In addition to this discussion, be prepared to both explain the significance of the V-speeds as well as define what they are for the airplane you're flying, either during this pre-flight briefing or during flight. You'll also want to have an explanation ready for how you'll estimate gliding distance in case of an emergency. Refer to your airplane's POH or Pilot Operator Handbook for this data.